How's it going? Okay, no problem. Okay, are there any questions on anything? What was it that y'all worked on Thursday last week? Four 4.2? No, it's with exponential functions and things like that. Applications of exponents. Hmm. Okay, I think what we'll do is we'll introduce the next topic, then logarithms today, section 4.3. Okay. So, for section 4.3, we're looking at the idea of logarithms, which are directly related to exponentials, but you may not realize that yet. Our basic function looks like this, where we have log b is written as a subscript, that's our base. Then x is written on the same line as logarithm. It's all good, Zoe. We just got started. And then x we refer to as the argument sometimes, just to have a name to call it. So that's our kind of our general logarithm right there. And it may be a equation y equals log base p of x instead of f of x. It could be a function or equation. It doesn't matter. We have two specific types of logarithms that we don't write the base for. And the base is written right here. If we have y equals log x, this is the same thing as log base 10 of x. And if we have y equals ln x, this is log base e of x. Ln is called the natural logarithm. Just like e is called the natural exponential, so it's a direct correlation to that. Okay. So in general, our base can be anything, but if we specifically have base 10, then we can just write it as log x. And if we have base e, we can write it as ln x, or natural log of x. But the real question here is, what does it mean when we take a logarithm? Okay. So if we have log base b of x, means that we want to find what power b must be raised to in order to equal x. So when we see log base b of x, it means what power b must be raised to in order to equal x. Just to look at some examples now. Let's see. I'll leave that there in case y'all write it down. So if we look at log base 2 of 8, for instance, when we see this number, or we see this expression, we have to look at it and say, okay, 2 raised to what power is equal to 8? Okay. So you want to know what that power is? Well, if you remember, 8 is 2 to the third power. So log base 2 of 8 would equal 3 in that scenario. Okay. Log base 5 of 25. Similar setup. Let's say 5 to what power equals 25. Okay. So 5 to what power equals 25? Well, we know that's 5 squared equals 25. So that means log of base 5 of 25 is 2. Then if we have log base 6 of 1 over 6, again our thought process is 6 to what power equals 1 over 6. This one's a little bit different, but turns out 6 to the negative 1 power is equal to 1 over 6. So, our conclusion is log base 6 of 1 over 6 is equal to negative 1. Okay. Last example. Log base 2020 of 1. This again means 2020 to what value, or to what power, equals 1. Remember, anything to the 0 power is equal to 1, as we investigated last week. So 2020 to the 0 power is equal to 1. So our conclusion is log base 2020 of 1 is equal to 0. Okay? 2020 to the 0 is equal to 1. So that's kind of what we're looking at with just our basic logarithms. I mean, that's how we consider them. Now this last one is interesting because it tells us something that's true for a lot of different logarithms. So we can say in general, log base b of 1 is equal to 0, since b to the 0 is equal to 1 for every base b. Okay, so anytime we try to take the log of 1, it's equal to 0. It doesn't matter what the base is in that case. Now, all these things that we did here, or logarithms in general, we can do a lot of our calculations on the calculator. We don't necessarily have to do them by hand if we have a calculator available. But there are others that we just won't be able to do without the use of a calculator. So if I ask you, log base 3 of 25, well, since 25 is not a power of 3, we can't really say exactly what that result is, but we do have a way of finding it out. So for calculations of logarithms on our calculator, we typically have two buttons. Not necessarily two, but we have two functions we can use. And this will be on a scientific calculator. We have log. This is our log base 10 button. And ln, which is our log base e button, or natural log as we refer to it. Now again, depending on your calculator, you may have some other options, or like you might have an option that allows you to find log of a different base than e or 10. But for the longest time, the only log functions you found on the calculator were log base 10, which is just the log button, and maybe log base e, which is our natural log button. On this calculator, you can see those are the two that I have here, log and natural log, ln. I don't know why it says ln instead of nl. I have no idea why the order is that way, but that is the natural logarithm. So we have these two buttons that we can use to calculate logarithms. Other calculators, such as this one, they only have one button, but you see it has both ln and log on the same button. So turning that on, if I press the button once, it brings up ln, and if I press the same button a second time, it brings up log, which is helpful in a way. If I press that third time, gives me log of a different base. So this is especially different from the previous one because it does allow us to find logs of multiple bases. But for the most part, people, I don't expect that you have a calculator that can have anything more than log and natural log. That's normally what we expect going into these things. Now the other issue that we encounter is, when we have a logarithm calculation, how do we enter that into the calculator? Well, first of all, it depends on your calculator. So some calculators, like if we wanted to find log of 10, now let's say log 20, that's better. We would either have to press log first, and then the 20, and then enter or equals, or on other calculators you'll have to enter the 20 first, and then press the log button. Okay? So the order turns out to be pretty important. Now, on this calculator, I know I have to press log first, then enter 20, and then press equals, and that'll give me a result, 1.301. And we'll usually round this to like 3 decimal places. Really just depends on whatever your professor specifies. Without any other context, three decimal places is generally pretty good. So this calculator, you put the log first. On my phone calculator, however, on this one I have to press the 20 first and then press log, and then it'll give me an answer. So it depends on which one you have. Notice if it just says 0 there and you press log and it says error, it means you tried to take the log of 0 and it throws back an error. We'll talk about why in a little while. But if you press log and it gives you an error, that means you need to enter the number first. That's generally how we tell the difference there. So, like if we wanted natural log of 10, we'd press 10 and then ln, and that would give us our answer. Alright. So one thing is it's nice to figure out early on is the method of entry that you need to use for your calculator, so that when you go through class you can practice that. That way you'll be able to try to get the same result that your professor is getting, and make sure that you're doing the calculation correctly. That's the main thing. It's good to practice that before you get into a test situation. So here we decided that log 20, let me just make a note of this. We said log 20 is approximately 1.301. So make sure you are able to get that on your calculator, just so you know that you are able to use the calculator correctly. Okay. The other one I mentioned was natural log of 10, and again, we either enter the 10 first and then press ln, or press ln first and then enter 10 and equals. This calculator will do natural log 10 equals, and that'll be 2.303 if we round. Okay. Now, the issue is then, what happens if we're given something like this, log base 3 of 10? Well, we certainly don't know just by looking at it. We can kind of take a guess because we know, we're saying basically 3 to what power equals 10. And we know that 3 squared is 9, so if log base 3 of 9 is 2, then log base 3 of 10 should only be a little bit bigger than 2. But we don't know exactly what it should be. Now, for this problem, we have what's called a change of base formula. And what the change of base formula does, this is log base b of x is equal to log of x over log of b. Now, it's also equal to natural log of x divided by natural log of b. Now, what that means is we have a log of some base that we cannot do in the calculator, usually anything besides 10 or e. Then we can turn into a quotient of log base 10s or a quotient of log base e's. Okay? When we use the change of base formula, we can change the base to anything we want. But in this example, I've shown you two different formulas for log of base 10 and log of base e, that both of those we can do on our calculator. So if we wanted to find log base 3 of 10, we would take log of 10 and then divide by log of 3. So whatever the argument is goes in the numerator, and whatever the base is, we'll take the log of that in the denominator. So we would do log of 10 divided by log of 3 equals. Now, some calculators are able to do that all in one step. Other calculators, you might need to put parentheses around the terms, like log of 10 in parentheses, and then divided by, and then parentheses log 3, and then equals. Because it's the same number on my calculator here, because mine is okay doing it either way. Other calculators, as I discovered in my algebra class, will not work that correctly without the parentheses. So you may or may not need to include parentheses, but again, this is why we practice it. We figure out these different aspects that we'll have to know how to use. And so this works out to be 2.096 after we round. Okay, but that's how we can apply the change to base formula to help us approximate these values. Even if we go back to all these other problems I gave you, like log base 2 of 8 was equal to 3, we could still do that. Log of 8 divided by log of 2, and it does give us 3 there. So we don't technically have to do that by hand if we can use the calculator to do that for us. Okay. But it's especially useful in these cases where we just do not know what the value is by looking at it, we can kind of guess. We're going to kind of approximate where it is, but to get the actual answer, this is where we need the change of base formula. Excuse me. So this is one instance where it's helpful. And if it happens that we need it to be in a specific form, we can change it according to this formula. Now, as far as the domain of logarithms go, logarithms can only be used to evaluate positive numbers. And that certainly affects the domain of these functions. Now, when we say positive numbers, that means not zero and not negative numbers. So on our calculator, if we try to take log of 0, it gives us an error. And if we try to take log of a negative number, it gives us an error as well. Because it's just not defined at those values. Log of 0 is something like negative infinity, depending on what side we're looking at, but log of negative numbers is simply just not defined. But in most cases, we just say it is not defined, and that's sufficient. So if we have f of x equals log base 3 of x, then x has to be greater than 0. That's our domain. So whatever is in here has to be bigger than 0. So if we have instead 2 plus log base 7 of x minus 3, in this case, to find the domain, we take x minus 3 and say that has to be greater than 0. Whatever follows the logarithm in the argument has to be greater than 0. And we just add the 3 over. We'll say x has to be bigger than 3. So for this function, we can only plug in a value of x as bigger than 3 in order for this to have an actual answer. So notice that whatever the base is does not affect the domain, and if we have a number added on the outside, that does not affect the domain either. In the range of these, it's basically all real numbers, so we don't ever have to worry about that. I don't know what do you know to what extent you looked at graphing for exponentials? I'm not going to dive into graphing, though. I will leave that for Mrs. Knisley. Because she may not cover it. I don't know to what extent she wants to cover it, so I don't want to do too much like that. Anyway, logarithms are kind of a strange thing. There is a direct connection, though, to exponentials, and we kind of alluded to that before when we're talking about these calculations of logarithms like this. We said, okay, log base 5 of 25 is equal to 2 because 5 squared is 25. It's the reasoning there is entirely based on an exponential expression. And that's how we came to the conclusion that this logarithm is equal to a specific value. And because of that, they're intrinsically connected. So let's explore that connection further. We have what's called our conversion formula. Which says that if y equals log base b of x, then b to the y is equal to x. And the opposite is true also. It could go either direction. So we could start with the logarithm and change it to an exponential, or we could start with an exponential and change it to a logarithm. And that right there is one of the main ways that we solve different types of equations, whether they're a logarithm or an exponential to begin with. That's one approach we can use to solve multiple different types of equations with logs and exponents. All right. So let's explore this conversion formula further and practice it a few times. So we have the expression 3 is equal to log base 4 of 64. And we want to convert this to exponent form. Now, when we convert this, we know that we look at our conversion formula, y equals log base b of x converts to b to the y equals x. Well, we can line up directly what each variable is standing for. So x is basically 64, b is 4, and y is 3. So when we change it around here to b to the y equals x, b, 4 to the y, 3, is equal to x, 64. And this is a true statement. 4 to the third power is 64. So we could also say 2 equals log 100, and we want to convert that. Now, there is no base written here, but remember, if there is no base written, it's one of two things. It's either 10 or e. Now, if it's log, that means it's a base 10. If it had been ln, then that would be base e. So in this case, it's not entirely necessary to write the base because the base 10 is implied when we leave out the number there. And that's because we use base 10 for a lot of things. We have a base 10 counting system, and ultimately that's why we like to use, we kind of use this as kind of our default because it's one that we use more often than others. Yeah. Converting that, for this, I kind of think of it like a pattern. That's how I remember it. I don't really, line it up with the variables and then convert it, although that's one strategy when we're first learning it that works really well. Um, I like to kind of visualize how things move around. The base here is the base over here. And that's why we call it the same thing, because it is the same thing. The base of the logarithm is the same thing as the base of the exponential. The only difference is here we have base b associated with x, and here we have base b associated with y. So essentially, whatever number the base is with here, it then gets associated with the other number. So we put 10 to the 2, and then the 100 is by itself now. So you can think of it as base raised to the opposite side equals argument. That's one way we can remember to convert that. Same thing here. 5 equals log base 2 of 32. And so that makes it 2 to the 5th equals 32. Now, it doesn't have to have just all numbers. In fact, a lot of the time when we need to use this conversion formula in the course of solving a problem, not all three terms are going to be numbers. We might have, for instance, 3 equals log base b of 27. We can convert that and say b cubed is equal to 27. B to the third is 27. 2 to the 5th is 32. 10 to the second is 100. 4 to the third is 64. This one, in this case, if we're trying to solve for b, we would convert it and then solve this equation now. In which case, we would just take the cube root of both sides and say b is 3. Similarly, we could have 4 equals log base 3 of x. So if we convert that, it's 3 to the 4 equals x. Whoops. I said it right, and then I wrote it. 3 to the 4 equals x. And that way we can actually solve for x. X is equal to 3 to the 4th, which is 81. So if the unknown is here, then we can solve for it here. And that's actually how we will end up solving some of these different equations that have logarithms in them. It's based entirely on this conversion formula. All right. Now the conversion formula does work both ways. Because we can also say that b to the y equals x becomes y equals log base b of x. This one's a little bit less intuitive if we're trying to switch it according to pattern. But again, we know base here is the same as the base here in the logarithm. And then whatever b is associated with here is now on the opposite side from b here. So if we have 2 to the x equals 10, and we convert that, x goes over here, and we have log base 2 of 10. Now we actually are able to solve that using our change of base formula, and we can actually solve for x that way. There's other ways we do that, but that's one way that we can do that. if we say that 5 to the third is 125, which is true, then we say when we set up our log, we know we have base 5, because base 5 here equals base 5 here. 5 is associated with the 3, so it's not going to be associated with the 3 here. So we'll put the 3 over here, and then the 125 goes in the last space that we have. So in that way, we can kind of think of it as a process of elimination as far as changing it from one form to the other. And so if we have something like 10 to the third is 1,000, we convert that over. It's log base 10. 10 is to the third here, so the third will be on the opposite side, and 1,000 will be inside. And we could also write that as 3 equals log 1,000. Because log base 10 is it's the same thing as just plain log. There's actually a bunch more formulas that we end up having with logarithms. Conversion formula is one of the more important ones. That's why I wanted to go over it first. But the other ones are also equally useful in solving equations and simplifying expressions, but I don't think I want to work on that today. I'll leave that for y'all to work on tomorrow. Again, we're just looking at the fundamentals here, not really getting into the more involved stuff, as it is. Let's see. Do you all have any questions? So when you look at the problems in the textbook here, you can see the very first questions that they ask us are translate each logarithm or translate each exponential into an equivalent statement of the other type. So change all these logs to exponents, change all these exponents to logs. So that's our conversion formula right there. And these they want us to find without using a calculator, which means it goes back to what we're talking about before, right here, where we thought about, okay, this to what power equals this number. So, for instance, 13 log of 1,000, that means, now, that, first of all, we know that there's a base of 10 there since it's not listed and it's log. So 10 to what power equals 1,000? And we know that's 10 to the third power. Or maybe we know that's 10 to the third power. That's not always obvious. Then log base 6 of 36. 6 to what power equals 36? We can figure that one out. And it's the same types of things that we were talking about. After that, they have you using a calculator, and then using some of the different properties beyond that. Okay, so hopefully that gets us through the first part of this section. That gives you a good basic understanding, so that when you talk about it some more tomorrow, it won't be a completely foreign concept. I find that logs and exponents is where a lot of our students coming into either college algebra or business math, this is where we start to get to the things that, at least in college algebra, that's where they kind of lose their comfort level as far as what they've seen previously. At this point, though, since we do logarithms last in business math, or at one of our last things, probably you already passed that point with all the matrices and financial formulas and things like that. Those are probably all completely new, so this is, I guess you're used to that by now, maybe, I don't know. But, anyway, so really what I'm saying is I don't have anything else I want to cover there. So does anyone have any questions? Okay. Alright. As I said, I don't want to get too far into it and steal all of Mrs. Nicely's thunder there. But again, I don't want to step on her toes either, because there may be a certain way that she wants to teach you something that I may be showing you a different way. And I apologize if I've messed you up here, but I did try to shy away from some of those other topics where she may teach them a little bit differently. So, anyway, I think we'll stop there. And remember, there's no class on Wednesday. So I will see y'all next week on Monday. And I think what we'll do on Monday and Wednesday next week is just look at the review for business math. And I'll take any questions you'll have on that, and we can go over that. You should have it by then, if not already. Anyway, so we'll stop there, like I said. Y'all have a good Thanksgiving. Maybe get a chance to rest a bit. That'll be good. I'm looking forward to sleeping in a little bit, a couple of days. Now, since I have 8 o'clock classes, sleeping in for me is sleeping until like 9, but it still feels pretty good. So, otherwise I just completely mess up my schedule. So. But I hope you'll have a good time, and at least and you get to enjoy some time off. Maybe you're not working too. That'd be great. So, I mean, having a job is great, but also being off from that job is great. So, y'all take care. Have a good one. Bye.